I am going to sort of try to weave together mitigation and adaptation, because I actually feel that we need to bring mitigation as the concept that is part of adaptation and resiliency building. And I'll focus on dairy manure. Our research, my research with Peter Woodbury covers a whole gamut. We have all kinds of fact sheets and papers, but I personally feel that dairy manure management is one of the lowest hanging fruits for mitigation and adaptation on farms. Across the nation, most of our greenhouse gases come from CO2, so 81%. It's almost the inverse on a dairy farm, and that is because methane and nitrous oxide have different global warming potentials. So the global warming potential, you probably all know, was developed to allow comparisons of the global warming impacts of different gases, and you compare them in CO2 equivalents. And this is really important. You'll see that methane, it has a lifespan of only 12.4 years in the atmosphere. So on a 100-year timescale, it's 34 times more potent than CO2. But on a 20-year timescale, it is 86 times more potent. And this is really meaningful. I'll come back to it later. Nitrous oxide, you'll see, is 300 times more potent on a 100-year life scale. So from my previous work with John Duxbury, where we looked at the feed production, transportation, enteric, and manure management emissions, CO2 only accounts for 25% of milk emissions. Methane accounts for 53%, and nitrous oxide accounts for 22%. So my point here is methane and nitrous oxide are the things we really need to be looking at. And of that, manure management accounts for 23% of dairy farm emissions. So manure, it has nitrogen, which leads to the production of nitrous oxide, and it has volatile solids, which lead to the production of methane. And what's fascinating is they have an inverse relationship. So in a more anaerobic or low oxygen condition, you have high conversion of the volatile solids to methane, and it prevents the conversion of nitrogen to nitrous oxide. The reverse is true in a more aerobic or high oxygen conditions, because that prevents volatile solid conversion to methane, but it promotes nitrogen conversion to nitrous oxide. So what's fascinating is manure has tons of volatile solids and a methane conversion factor of 34. Manure has significantly less nitrogen, but a global warming potential conversion factor of 300. So it gets complicated, depending on which manure management strategy you use. Daily spread, what we typically have done historically, is aerobic. And you have high nitrogen loss from a winter field, but you have low methane production. With liquid storage, it is anaerobic, so that we have installed that to improve water quality across the state. And that's great for retaining nitrogen in the liquid manure so that you can apply it in the spring. However, you have massive methane production in liquid manure storage. So this is the research context. So Peter and I got a grant, and the basic idea was farm size was increasing, larger farms using best management practices and CAFO rulings were forced to use more manure storage to protect water quality. As a result, more anaerobic storage then resulted in increases in methane. And our questions were, how do policies to improve water quality right, regulated, impact unregulated greenhouse gas emissions? Is there cost-effective ways for addressing these new GHG emissions? And do extreme weather events threaten water quality now with manure storages in place? So this is just farm trend size trends, and the smaller farms are decreasing and the larger farms are increasing. That means there's more liquid manure storage. Here you can see in 1992, top left, 80% of the manure was daily spread. In the middle, you can see 2012, almost 50% of the manure was stored in liquid storage. And you can see highlighted in yellow that the megagrams of CO2 equivalents from 1992 were 702,000 megagrams of CO2 per year, and it doubled in 2012, okay? What I'm trying to get at here is 80% of manure management emissions come from methane, and more anaerobic storage means more methane production, and we have doubled our emissions from New York dairy farms, right? So our policies to store manure while protecting water quality resulted in a doubling of GHG emissions. However, it's a little bit more complicated, of course. So we compared the 1992 and 2012 herd with the manure practices. So this is just methane, there's no nitrous oxide. And if you look in the gray box, the 1992 herd was 500,000 and the 2012 herd was 1.2 million, 1.3 million. If we took the 2012 herd and applied the 1992 daily spread practices, right? The emissions dropped to less than 500,000. The point being here is that dairy farmers have been increasing feed efficiency, which has been reducing both enteric and manure emissions, right? So what I'm trying to note here is dairy farmers have been making great progress on feed efficiency, which then has reduced the amount of manure that's going into the storage, right? But that's sort of obfuscated because we see a doubling in greenhouse gas emissions overall. So what can we do with that? Well, with the cover and flare system, which is what I'm going to advocate for the rest of this talk mostly, you can capture the methane that is produced and you can destroy it. And when you flare methane, it goes from a 34 factorial of climate change global warming potential down to 1, right? You've just oxidized it. Additionally, if you burn that methane for energy generation in an anaerobic digester system, then you're displacing fossil fuels, right? So here's a cover of a manure cover and flare system in Pheasant Farm, which is in New York. And so we did a bunch of, some scenarios for 6 months storage for a 1,000 cow farm and a 550 cow farm. And so the total cost for cover with where you separate solids and you pay for disposal and you pay for interest, for a 1,000 cow farm would be about $380,000 versus $270,000 for a 550 cow farm. So I just want to compare a little bit. A cover costs around $300,000. It also reduces odor. It improves nitrogen management. It prevents extreme weather events from causing overflows. It reduces hauling costs because you're no longer hauling rainwater. And it also decreases greenhouse gases. A $1 million anaerobic digester system does that also. But in addition, it generates some electricity from the combustion of that methane. So why am I so passionate about methane destruction as a constructive next step? Because everything we do right now to destroy methane is going to slow the curve, the whole large curve, right? On a 500-year timescale, the fact that a 12-year lifespan methane has a factor of 7 should be astounding. Is everybody kind of getting this? So everything we do to destroy methane today has multiplicative effects into the future, right? Because increase in temperature will also result in increase in methane production. So if we have a longer, warmer season, we will also have more methane production, right? So whether or not we cover these manure storages, we will be producing more methane, which then has the positive feedback. It also means that the cover and flare values will have a higher cost effectiveness. Because increases in precipitation can cause uncovered storages to have overflow events. So for example, in New York, winter, spring 2017, there were unusual volumes of precipitation. And if you don't have a covered storage, right, they were getting filled to capacity. And we had approximately 15 storage overflow events. That means violations of permits, right? Where the storage unit overflowed and contaminated local water resources. To be fair, one might also imagine what happened to the farms that continue to daily spread in that incredibly wet season, right? Like, I don't mean to say that this is terrible about manure storages. I'm saying when you plan for a manure storage, you have to plan for the amount of rainwater that is coming also. And if you don't, you can have a violation. Also, because some farmers are voluntarily doing it for other reasons. Odor control, community relations, increased storage capacity, right? If you already have a storage and you retrofit it, you no longer have to worry about your rainfall amounts and you can increase your manure storage capacity. And also because you have decreased hauling costs. And this is a real thing that farmers are thinking about. They don't have to haul the rainwater, right? And the manure is more concentrated, so they can be more specific and less or more intensive about their application. Additionally, I would argue it's a helpful step towards developing an anaerobic digester system so that when the price for energy becomes better, they are already well trained in methane capture and destruction, dealing with hydrogen sulfide, which is toxic, that builds up, and also a storage unit. After the digestate comes out of the ADS, it has a covered storage spot. So I just want to add one thing, which is I'm kind of a stickler for this now seemingly old EPA idea of what we should promote, that we should promote real, additional, permanent, and verifiable reductions. So my point being is that if you receive federal, state, or local funding, projects should be real. That means actual emissions reductions. Projects should be additional. It is an action that goes beyond business as usual. Projects should be permanent. That means that the mitigation is non-reversible, and projects should be verifiable. They are readily and accurately quantified. Don't we all want our tax dollars to work fast and effectively to slow the curve of climate change, right? And so what I've done here is sort of made a chart to go through certain practices specific to manure, right? You can do this with all the other practices, but I've just focused on manure today. If you do dairy feed management, right? Dairy feed management reduces the enteric methane emissions, and it reduces the amount of manure produced, thus reducing the production of manure methane. Is that real? Absolutely. Is it additional? No, because you save money in feeding your cows less feed, right? So do you need to get funding for dairy feed management if you're saving money and being more efficient in your feed allocation? No, but look at all these incredible positives that happen when you do so. You have water quality impacts, you have decreased dollar inputs, you have increased milk profitability, you have reduced land area requirements for both growing and for manure application because you produce less and you ate less or you fed less, and less corresponding downstream effects. You have reduced manure spreading, and you've also addressed greenhouse gases reductions. If you reduce the nitrogen in the diet, is this real? Yes. Is it additional? Yes. Is it permanent? A little bit more difficult. Is it verifiable? A little bit more difficult. But what are the positive impacts? You have water quality improvements, plus you have reduced nitrogen in the manure storage to produce N2O, both in the storage unit, but also after you apply it to the field at inappropriate times, because sometimes you have to do that. How about separated solids with the roof? Now this is complicated because there's possible methane mitigation, but likely negated by nitrous oxide emissions, right? You have your solids, it's somewhat aerobic and somewhat anaerobic, and we have the battle of the conversion factors and the global warming potentials of methane and nitrous oxide. But it also has benefits. The separated manure liquid storage with cover, this is real, additional, permanent, and verifiable. It has a huge suite, and I feel like I should not read them because I'm short on time. But the point here is New York State just last year initiated funding for covers and flares specifically because it is real, additional, permanent, and verifiable with all these other benefits, right? Like, this is a solid solution. If we add anaerobic digesters, you'll see it's the exact same list in addition to the fact that you're producing renewable energy. So, my top 4 practices for whole farm resiliency, short and long term. Farm forests for long-term profitability. 30% of farm acreage is in forests. We should be managing them fiercely. Methane destruction on dairy farms, end use efficiency, and renewable energy.